and welcome to DNB 313 Advanced CAD. My name is Tim Williams, and today I'm going to talk to you about dimensional tolerancing. Whenever you have an assembly of parts, it's really important to make sure that the parts are dimensioned in a way and manufactured in a way so that they will fit together. And the way that we communicate our design intent is through geometric tolerancing. So for example, imagine you've been asked to cut some logs with a chainsaw into 750mm lengths. Now, chainsaws aren't the most accurate way of cutting timber, so how likely do you think it is that you'll be able to get 750mm long lengths? If you're very careful and very skilled with a chainsaw, you might be able to come up with a list of lengths that looks something like this. So as you can see, only one is actually 750mm long, the rest vary by a little bit either side. If we plot those lengths on a graph like this, we will see that the maximum size is 765mm and the minimum size is 735mm. Those maximum and minimum are both 15mm either side of the 750mm line. So we can express that by writing 750mm plus or minus 15mm. So on the graph we can see we have a band that goes either side of the 750mm line by 15mm either side. When we have a tolerance like this, 750mm plus or minus 15mm, this is what's known as a symmetric tolerance. So the tolerance is symmetrical around the base dimension of 750mm. But what if we were only going to get paid for the logs that were within 10mm of our 750mm specification? If this was the case, then we would find that 4 of the logs were outside of that tolerance, and therefore we'd have to reject them. So we could either throw the logs away, or we could find a better way to cut the logs more accurately. And that would mean probably more equipment, probably a longer time, and will cost more money. Or we could reject the logs, which would also cost more money. So the tighter and smaller that tolerance is, the more expensive the processes become. But there are other ways of tolerancing something. For example, we can have a bilateral tolerance. What, for example, if our logs needed to fit in a box that was 760mm wide? We set our base dimension at 750, which is what we really want. We could allow the logs to be up to 10mm longer, and we'd also have a specification where we'd allow them to be 15mm shorter. So what that would look like is that we need to have a maximum size of 760mm and a minimum size of 735mm. That means 3 of the logs wouldn't fit, and we have a slightly different tolerancing system. What we now have is a 750 plus 10 minus 15 tolerance. If we plot that on the graph, it looks like this. This is what's known as a bilateral tolerance. There is another way of creating a tolerance, and that's known as a limit tolerance. And in this case, you simply put the upper limit of what you want above the lower limit. So in this case, the 760 is the upper limit size-wise, 735 is the lower limit. Now, this isn't used as much as the other 2 tolerancing systems because what it doesn't do is tell you the dimension you really want. So in the other 2 cases, I really want to have 750mm, but I'll allow some leeway on either side. In this case, you're quite happy with anything that's within that limit. So just to recap, I've covered the 3 main decimal tolerancing systems. So we have symmetric tolerances, for example, 25.5 plus or minus 0.5. We have bilateral tolerances, 25.7 plus 0.3 minus 0.7. Or we can have limit tolerances, 26 over 25. Now, all those numbers will produce exactly the same results. So the question is, why use one system over another? And the reason for that is because with the symmetric and the bilateral tolerances, they give you an ideal dimension. So with the symmetric tolerance, ideally we want 25.5, but we'll allow some variation of 0.5 either side. With bilateral tolerances, we really want to have 25.7, but we'll accept plus 0.3 or minus 0.7. With limit tolerances though, you can put that dimension anywhere between 26 and 25. So how do we set tolerances? Well, as I said before, the more tightly held a tolerance is, the more expensive it's going to be. But this depends very much on the manufacturing process that's being chosen and the materials that are being chosen to be manufactured. So for example, wood can be machined to a very high tolerance, but it's not as high as metals or plastics. Maintaining a very tight tolerance is not easy. Metal, on the other hand, can be precision ground to extremely high tolerances, up around the 0.002 of a millimetre. That's 2/1000th of a millimetre. CNC or human-operated mills or lathes can achieve a tolerance of around 0.05 of a millimetre. An injection moulding, typically for a length part of around 200 millimetres, you can get a tolerance of about 0.1 of a millimetre. By comparison, rotational moulding is very difficult to hold high tolerances. So with a product that's around, say, 3 metres long, let's say a rainwater tank or a kayak, you're lucky if you can get plus or minus 5 millimetres. To minimise cost as much as possible, it's really important that you specify the largest possible tolerance that your design intent will allow. So for example, most door panels in cars will have a gap of between, say, 3 to 5 millimetres. Now the tolerance on that gap will probably be plus or minus 1 millimetre. Every dimension you have on a drawing needs to have a tolerance. And that's because, as I said before, it's impossible to make something exactly to size. So what often happens though is you'll see dimensions that don't have tolerances next to them. And quite often they will have tolerances because the tolerance will be driven by what's known as the general tolerance system or the decimal tolerancing system. So you'll often see in the title block a line that says general tolerance and then a series of tolerances next to 0 decimal, 1 decimal, 2 decimal and so on. So let's look at what that means. So on the top right hand side we've got 3 dimensions. One dimension says 10, one says 10.0, the other one says 10.00. Now if there is no tolerance associated with that, those dimensions are exactly the same. They're all 10, right, regardless of how many zeros. But with the general tolerancing system, if we have 0 decimal places, we apply a tolerance of plus or minus 0.5. If we have 1 decimal place, we have a tolerance of plus or minus 0.2. And if we have 2 decimal places, we have a tolerance of plus or minus 0.1. Now this will vary depending on what you're drawing. This is just an example. But it means that we actually have a different tolerance depending on the number of decimal places. So it's really important that when you're creating a drawing, you put the correct number of decimal places onto your dimensions. Controlling the number of decimal places on your dimension is very simple. So firstly, we'll just put a dimension on here. And as you can see, by default, it's got 2 decimal places. We can just quite simply go over to, we can click on that dimension if it's not already selected, and we can go over to where it says tolerances and precision. This is where we put our tolerances on. In this case, if we have general tolerances, we don't need to have additional tolerances on the actual drawing itself. Now typically, if there is a tolerance on a dimension and there are general tolerances, the tolerance on the dimension itself is the one that takes precedence. So to change the number of decimal places, we can just select, by default, the document has 2 decimal places. If we go to 1 decimal place, we can select that, or we can say no decimal places at all. So 0 decimal places will be plus or minus 0.5. If we go to 1 decimal place, that will be plus or minus 0.2. So that now means that this dimension of 21.3 can be either 21.5 or 21.1. Now you might find that when you put a dimension on your drawing, for example this one here, it gives us a radius of 30. Now we might want to have a tolerance, we might want this to be 30.0 or 30.00 to give us the 2 decimal places. So normally we'll just go over to the number of decimal places and select 2 decimal places, hit OK, and this should update the number of decimal places. But there's a setting in Tools, Options, Document Properties, and then we go down to Dimensions. There's a setting here that says Remove Trailing Zeros, so that stops you from having 30.0. If we go to Show, hit OK, now we've got our 2 decimal places. How do we calculate the tolerances on various components? The most important thing is to work out which are the critical features. So these features are the features that will interact with features on other components. And for that we need to calculate what the maximum and minimum conditions are for both of those features. So we need to do this for not just size but also position of the mating features. So for example, in these 2 very simple parts, we have a plate with a peg on it and we have another plate with a hole. Now ultimately we want the peg and the hole to be 15 millimeters in diameter. But as we've discovered, we can't just specify 15 millimeters because there will be a tolerance and it will vary from 15 millimeters. We need to calculate what happens when the peg is at its largest and it's at its smallest, and when the hole is at its largest and its smallest. So obviously the peg can't be larger than the hole or it won't fit. So we want 15 millimeters, and the easy way of doing that in this case is to say that we want to have a peg that is 15 millimeters in diameter, and it can get a little bit smaller but it can't get any larger, and the hole is 15 millimeters in diameter. It can't get any smaller but it can get a little bit larger. If we've got a tolerance band of 0.5 millimeter, the hole therefore will be 15 millimeters minus nothing because it can't get any smaller, plus 0.5 because it's allowed to get larger, and the peg will be 15 millimeters in diameter minus 0.5 millimeter, 0.5, and plus nothing because it can't get any larger or it won't fit. When the peg is on its smallest size and the hole is on its maximum size, we'll have the maximum amount of clearance, and in this case it'll be 1 millimeter clearance because it's 0.5 for the peg and 0.5 for the hole, which gives us 1 millimeter overall. What I've just shown you is a very simple example of how to create size tolerances. But we also need to create position tolerances to position the locating features in our parts. Again, a simple example where we have a plate with 2 pegs and we have another plate with 2 holes, and of course the pegs and the holes need to line up. This is pretty much as simple as it gets, but as you'll see, it can become complicated fairly quickly. Remember, we still have to have tolerances for the size of the pegs and the holes, and as we calculated before, the maximum size for the pegs and the minimum size for the holes will give us good fit. What we also need to consider though is the position of those holes, and of course the position on the holes and the position on the pegs will both have dimensions and both be toleranced. So in this case the holes can be 60 millimeters plus or minus 0.2, and the pegs will be 60 millimeters plus or minus 0.2. So if the holes are as far apart as they can be, they could be at 60.2, and if the pegs are as close together as possible, they can be at 59.8. So that's a difference of 0.4 of a millimeters. Now if our pegs and our holes are in the closest tolerance that they can be, there'll be an interference because the holes and the pegs won't line up. So what this means is we need to increase the tolerance between the pegs and the holes by 0.4 of a millimeter. That gives us a little bit more clearance around the pegs and the holes. Another important concept to understand when dimensioning a part is the concept of tolerance stack-up. In this example, all the holes on the top are dimensioned from the center line of the adjacent hole to the center line of the hole that we're dimensioning. And on the bottom we have holes which are dimensioned from what we call a datum, and the datum is just simply a common thing that we're dimensioning from. In this case, the edge of the left-hand side, and every dimension is related back to that. So all the dimensions on this sheet are plus or minus 0.5 millimeter tolerance. The ones on the bottom, though, are all tolerance from the same datum, which means that this is a far more accurate way of creating a tolerance, because all the holes in the upper side might be on the maximum tolerance, which would mean that the hole on the right hand side might end up by being 92.5 millimeters away from the left hand edge. If all the holes at the top were on the minimum tolerance, we would have a situation where the top right hand hole would be 87.5 millimeters. So we have a variation of 5 millimeters between the maximum and the minimum possible conditions. With the holes on the bottom, though, the bottom right hand hole will only ever have a variation of 0.5 millimeter, so it will only vary between 89.5 and 90.5. There's one other thing I'm going to mention, although not in great detail because it's a very large topic and we really don't have time to cover it in this session, and that is geometric tolerancing. So geometric tolerancing not only sets size and position of components, but it can also set the geometric conditions of those components. So for example, our plate that has the two pegs attached to it, we can define how flat the plate needs to be. We can define how parallel the two pegs need to be. We can define how cylindrical the pegs need to be, and so on and so on. So we can define every aspect of that component. And as I said, this becomes quite complex, and so we really don't have time to cover it in this session, but it's certainly something to be aware of. If you see symbols on a drawing such as this in little boxes, in this case we have two datums A and B, and we have a positional tolerance that relates that hole to the two datums A and B. But as I said, that's probably all you need to know. This is something that exists, and that if you see this on a drawing, you'll know that that's something you need to look up. There's a lot of things to think about when creating tolerances, and this is just a brief overview. Some of the rules of thumb to consider, though, is that for features of mating components, try to use the same tolerance. With injection molded parts, it's also important to err on the side of caution and to leave extra clearance between parts, because it's much easier to remove metal from a tool, and that equals plastic on the part. Therefore, it's fairly easy to reduce the clearance and tighten up the tolerance if possible. This is what's known as a metal safe condition. So that's probably all you have to really worry about at this point in your career when it comes to dimensional tolerancing. It is one of those topics that's quite complex, and that in future you probably will have to learn a little bit more, but it is one of those topics that you can learn as you go along. So thanks for listening.